Welcome to Maths for All. I'm Aisling Flynn. This is Number Patterns 1.5, Non-Linear Patterns. Consider this first pattern, 2, 5, 10, 17. We're going to examine the differences between terms. So in the first column we have our sequence 2, 5, 10, 17. Let's look at the differences between the terms. So from 2 to 5 is plus 3, from 5 to 10 is plus 5, from 10 to 17 is plus 7. Okay, so clearly the first difference is not constant. Okay, and if we were to put that on a graph, it would not show a straight line, so it is not linear. Or not, the other word we used for linear was arithmetic. Okay. Now, clearly though, there is a pattern. 3, 5, 7 are the first differences. So if we look at the difference between those, 3 to 5 is 2, plus 2, and 5 to 7 is also plus 2. So we say the second difference is constant. The second difference is constant, and so if we wanted to find the next few terms, we could. And these type of sequences are known as quadratic sequences. In this particular case, the general term Tn is given by n squared plus 1. So a quadratic sequence, the general term always has an n squared part to it, and the word quadratic refers to the square part. Okay. And on a graph we said it will not look linear, will not be a straight line. Instead, they start slowly and they will tend to show a curve, so starting slowly and increasing more rapidly. Why? Because numbers, as you square them, get larger and larger. Okay. Find the next two terms of these quadratic sequences by finding the first and second differences. Let's look at the first example. From 3 to 4 there's a difference of plus 1. From 4 to 6 it's plus 2. From 6 to 9, 3. From 9 to 13, 4. So clearly it's not linear. The first difference is not constant. But there is a pattern. Let's look at the second difference. 1 to 2 is plus 1, 2 to 3 is the same, and 3 to 4 is the same. So the second difference is constant, so you conclude that it's quadratic. Okay. So to get the next terms in the sequence, well, the next addition would be of a 5, wouldn't it? Okay, so 13 plus 5 makes 18. And the next one after that would be to add 6, and that gives us 24. Okay, let's look at the next one. Plus 3, plus 5, plus 7, and plus 9. So not linear, first difference not constant. But if we look at the second differences, 3 to 5 is 2, same from 5 to 7, and same from 7 to 9. So second difference is constant, so it is quadratic. So what would we add for their next term up here in the sequence? Well, we'd be adding 11 next. Okay, 27 plus 11 brings us to 38, and the next addition would be of 13. So 38 plus 13 is 51. Okay, so it's a bit like working backwards. Okay, let's look at the next one. Plus 5 from 2 to 7, plus 7 from 7 to 14, then plus 9, we see where this is going, and plus 11. So again, not linear, first difference is not constant, but the second difference is plus 2. Okay, so for the next term you'd add 13, so it's 2 bigger than 11, and we'd get 47. And for the next one you'd have to add 15, so 57, 62 would be there. Okay, and yes, it is quadratic because the second difference is constant. Okay, let's look at this sequence, 2, 10, 30, 68, 130. So no obvious pattern when you look at the numbers first. And let's examine the differences. I've done those in a table here. So first difference, 2 to 10 is 8, 10 to 30 is 20. We've got 38 and 62 as the first differences, so not constant, so not linear. Okay, or arithmetic, as we sometimes call them. Okay, still no obvious pattern appearing, so we go to the second difference. Okay, so from 8 to 20 is plus 12, 20 up to 38 is 18, and 24 brings you up to the 62. Again, the second difference is not constant, so it's not quadratic either. Okay, but a pattern is emerging: 12, 18, 24. So to get from one to the next of those, 12 to 18 is plus 6, 18 to 24 is also plus 6. So the third difference is constant. Okay, and these are what we call cubic sequences. Okay, the third difference is constant. This is a cubic sequence. In this particular case, the general term is n cubed, so n to the power of 3 plus n. So cubic sequences have a general term that has n to the power of 3, which is n cubed. That's why we call them cubic. Okay, and on a graph, okay, it's definitely not linear, but cubic sequences, they will begin more slowly and then they increase very rapidly, because when you cube large numbers, so when you get to larger terms, the numbers get much bigger very quickly. Okay, let's look at this example. Each layer of cubes in these designs is a square. How many cubes will be in model 4? Use the pattern to write down the number of cubes in model 5, and so on. And then we have some algebra to do. Okay, so let's look at model 2. I'm first going to write how many cubes in each sequence. So here you see I have 1, just 1 by 1. Okay, here you see I've that same one here, but underneath is a layer of 2 by 2, which is 4. Okay, so I've got 5 there. We'll put the total in circles. Okay, and in this one you see I've the 1 plus the 4 plus 3 by 3, which is 9. Okay, so 1 plus 4 plus 9 is 14. So if we take it like a layer approach there, and there's sometimes individual patterns you see it immediately and sometimes it takes a bit longer. So what do you think we'll have in model 4? Well, at the bottom, if we start at the bottom, we should have, instead of 3 by 3 here, we should have 4 by 4. So that will give us 16 on the base layer. And then we pile on top of it what we had in model 3. So we'd have 16, then 9 sitting on it, 4 sitting on it, and 1 at the top. So to get the answer, we'd add all those numbers. Okay, or it's 14 with an extra 16, we have 30. Okay, so so that's our first question there. How many cubes will be in model 4? And the answer is 30. Now let's look to question 2. Use the pattern to write down the number of cubes in model 5. Right, so let's take the same approach. On the base this time, on the base layer, there'd be 5 by 5, which is 25. And then we'd have our 16, our 9, our 4 and our 1 sitting on top of it. We know that that's adds to 30, so 30 and 25 gives me 55 for model 5. Okay, now question 3, show, this word here, show that the expression n over 6 by n plus 1 by 2n plus 1 gives the correct number of cubes in model 3 and model 4. So this is just to demonstrate that this formula works. We don't have to understand where it comes from at first. So we're doing model 3. Okay, so we put in the number 3 instead of n. 3. So every place n appeared, we put in the number 3. 2 times 3 plus 1. So we are substituting, and then we'll evaluate. So firstly, there's loads of approaches we can take here. Let's simplify where possible. 3 over 6 can simplify to 1 over 2, or half. 3 plus 1 in the bracket becomes 4. 2 3s is 6, and 6 plus 1 is 7 in that bracket. So multiplying the top line, 1 by 4 is 4, 4 by 7 is 28 over 2. So I get 28 divided by 2, 14. And is that correct? If you look back to model 3 up here, yes, model 3 had 14. So the word show here is asking you to demonstrate that the formula works for these numbers. We have to repeat it now for model 4. So replace n every place with the number 4. So that's substitution done. Simplify where possible. That's 2 over 3. You don't have to, but you can. 4 plus 1 is 5 inside the bracket, and 2 4s are 8. 8 plus 1 is 9. Okay, so multiplying the top numbers, 2 by 5 is 10, and 10 by 9 is 90. We get 90 divided by 3. We get T4 is 30. And looking back to our model 4, yes, we got 30. So we have shown or demonstrated that that formula works. And part 4, use the expression for the nth term to find how many cubes are in model 10. So that's just the same exercise again, but we're replacing n with 10. So we have 10 over 6 by 10 plus 1 by 2 10s plus 1. Evaluate now. I get 5 over 3 by 11 by 20. 2 10s are 20 by 21. So we might use our calculator for this one. So we'll have 55 by 21 on the top line. Okay, 1 second now, we'll calculate that. 55 by 21, so 1000. Where's my pen now? 1155 on the top line divided by 3. So let's divide that by 3. And I get 385 as my answer. Okay. Now, nonlinear patterns. Now, here's another one. 1, 2, 4, 8, 16. Okay, I think I see a pattern, but let's examine the differences. So, 1 to 2 is 1, 2 to 4 is 2, 4 to 8 is 4, and 8 to 14 is 16, right? Not constant, so not linear. Let's go to the next level. 1 to 2 is 1, 2, and 4. So, second difference is not constant. All right, so can you see that we are just repeating ourselves, that the third difference is also not constant. So, and as long as we continue in this matter, we will never get a constant difference. Okay, so addition or arithmetic is not going to work. Okay, so the differences are not constant. This sequence is gotten by multiplying. So instead of adding, we're multiplying, and you probably spotted it. We're multiplying by 2. Okay, so 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. You can see how it's going to go. We'd get 32, 64, 128. That's how it would go. Okay, so this one is not by the differences, not by adding or subtracting, it's by multiplying. And these ones are called exponential or geometric sequences. Okay, exponential because you're multiplying by 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. Okay, or that the numbers grow very large very quickly. If I was just to continue a few more, 128 by 2 is 256, 512, then you're into the thousands very quickly. Okay, so the numbers grow exponentially, they grow very quickly. In this case, the general term is given by A, which is the first term, or, which is your common ratio. In this example, or is 2. So the ratio is whatever number you multiply by each time to the power of n minus 1. Okay, at ordinary level, you're not asked to work too much with this. You're just asked to identify it and maybe find the next few terms. Okay. And if we're to look at a geometric sequence or an exponential sequence on a graph, you see it starts off slowly, but it increases really rapidly. Okay, so this is just by the 9th term, it has really shot up. Okay. Now it's time for you to look at some of those with your number patterns 1.5 quiz, nonlinear patterns, and the matching written exercise. And here's a bit of a glossary for you to look at as well.